Anton Ponomarev, and this is my project for CS230, ranking financial assets using neural networks. So I've been working in finance for almost a decade now, and I see how machine learning and deep learning specifically are disrupting the industry. However, in my honest opinion, the breakthroughs that can benefit everyone are yet to really happen, and mainly it's because the applications right now require access to large data sets, either high frequency data or alternative data sources like social media or news headlines. And these are really only accessible to sophisticated investors or academics, which is coincidentally why where most of the published research is focused on. So in this project, I wanted to explore a potential approach to predicting time series that would not require a lot of data or compute for that matter. So while the existing work to date has been about predicting future price levels or changes to individual assets, I propose to rephrase the problem slightly as follows. So given a set of assets N and a desired investment horizon H, select the asset that will deliver the best performance if held over the investment horizon H. To do that, I chose to use daily prices of publicly traded securities, which again are easily available to everyone. The data is cleaned, processed to generate training examples where X is basically a set of daily returns for each asset over some look-back period T, which also is a hyperparameter, and Y is the index of the asset that has the highest cumulative return over the defined investment horizon H. It feels natural to convert the label into a one-hot vector representation, so this effectively becomes a supervised classification problem. There are a number of architectures that can be used for this type of problems, and I have explored a number of them. I started with using just fully connected layers, and then moved on to also adding convolutional layers, because you could also think of the dataset X as pixel values of a picture that you can slide the filter over. And finally, I used the LSTM networks, which are very well suited for dealing with sequences. And in the end, so far, the results show that LSTM is superior. The issue I faced with the other two sort of approaches is really, I think, is rooted in the how much data I have available and the complexity of the inference that I'm trying to get the model to learn. So if you think about it, there isn't really that much data available for public companies, maybe 20, 30 years. And the actual relationship between that data and how does that relate to relative performance of the assets is quite complex. So what I found is that the network either learns very slowly or it overfits the data, and in both cases it basically does not generalize well, and that's particularly true for the fully connected network architectures and also convolutional networks. With LSTM, I found that I managed to train the network without overfitting the data, and in fact the test accuracy tends to be pretty close to the training set accuracy, with obviously some oscillations around it. And the longer you train the model, the higher the volatility becomes. But even up to 500 epochs, I haven't really seen the two deviate too much. So I'm hoping that the architecture in future work can be tweaked even further to improve both the fitness of the training set, and hopefully that will drag the testing set with it. And that's really all I have time for.